You know, so I think what I need to do is kind of, I think we did a good job in 5.2, which is exponential functions. And so now I want to move on into sort of, like I said, the rest of this chapter if I can, kind of. But I definitely need to start in 5.3 and tell you about logarithms. Now we had a little sneak preview of what logarithms are kind of used for last week. That was cool. But I kind of want to just start at ground level and teach you what a logarithm is. So I'm really kind of starting here in 5.3. And but to teach you about a logarithm, I want to talk about this first. So this is not a logarithm. This is just another exponential function. We've been dealing with exponential functions, different bases. You know, we've dealt with a base 2, we dealt with a base 3. We learned about base E. That was pretty cool. We definitely liked base E. But here's a base 10 exponential function. Listen, you guys know, well, if you've been coming to class and listening, you know about these exponential functions. I could plot some points, but yeah, in fact, I think I will plot a few points, but I kind of got past the point of plotting points. We got to where we kind of knew what this looked like. But real quick, if you plug in a -2 and a -1 and a 0 and a 1 and a 2 and a 3, let's just start with the 0. Plug in a 0, tell me what you get, please.
1.
Thank you, that's good. We've been good. Good job. Plug in a 1, what do you get?
10.
10. Plug in a 2, what do you get?
100.
100. If you remember, maybe you sort of remember that whatever the base is, that's what you kind of multiply by every time, it looks like here. Because 10 to the third is 10 times 10 times 10, which is 1,000. It's 10 times this. Anyway, and if you're going down the chart. If you go up the chart, maybe you divide by 10. If you plug in a -1, -10 to the -1 is 1/10. It's not -10. When you plug in a -1, it moves it to the denominator. It's a 1/10. Your calculator would help you with that. And if you plug in a -2, can you tell me that one? 1/100. Because it's 10 to the -2, it's 1/10 squared.
Okay.
Is how it works. So it's 1/100. Yep. Anyway, if I plot these points here, 0, 1. I mean, this is you're getting bored with this. Maybe 1 is a 10. 2 was 100. I can't even plot that. -1 was a 1/10. -2 was a 1/100. So it's this very typical, pretty steep though. It's pretty damn steep because of the 10, by the way. They're all steep, okay? Last week we had a 2, base 2, we had a base 3, we had a base E. They're all steep. They're exponential functions. They're very steep exponential growth. But with the base 10, I guess he's even a little steeper, okay? He's a little steeper. But that's it. There's an asymptote here. And, you know, good old exponential growth. Now let's play this game. To teach you about logarithms, now here's what I want. I want the inverse of this. If I want the inverse of this, now this takes me back to 5.1, but if I want the inverse of this, I had a method for getting the inverse. The Smith method doesn't work too good here. We'll toss that aside. There was a book method for finding an inverse. Do you remember what it was? Step 1, switch your x and y. So if I switch x and y, so now I'm looking at his inverse. His inverse is if you switch x and y. Well, that's easy. You put the x there, and you put the y up in the exponent. And you've just switched x and y, and now this is the inverse function. Except step 2 was always, let's solve for y. And this is where we need a new concept, because if you could go through your vast algebraic knowledge and you'll never come up with a way to solve for y. You won't. Divide by 10 doesn't work. Square root of 10, subtract of 10, square root of 10. None of that crap works. The way you solve for y is you have to unbase 10 it. Anyway, you need a new concept, and the new concept is logarithm. So that's my explanation of how you solve for y. The way you solve for y is you need a new concept called I'm going to do the logarithm of both sides. And I'm going to do the log base 10. There's all kinds of logarithms. There's log base 2, log base 7, log base 3. I think last week we learned about log base E. That was a special one. We called it the natural log. Remember that? But anyway, this one's not the natural log. We're going to go with log base 10. And to solve for y, I take the log base 10 of both sides. I take the log base 10 of the x. When we have a base on a logarithm, we write it as a little subscript. It's just a little subscript to tell me which kind of logarithm I got. I could have a log base 2, I could have a log base 7, I could have a log base 10. So I took the log base 10 of that side. When I take the log base 10 of this side, it cancels the 10 and it leaves me with y. So it's almost like you learn how to rewrite this thing. It's almost like I rewrote this, but these are equivalent statements. And now what we have is the inverse of this function. This function was y equals 10 raised to the x. This is y equals log base 10 of x. Some students get confused with this little lecture. They think, oh, this is the same as this? Nope, I'm not trying to say they're the same, but they're cousins. They are inverses. They're not the same, they're inverses. Well, I guess the main reason you can tell they're not the same is, look, this has y equals 10 to the x, this has x equals 10 to the y. I mean, right there, the x's and y's are switched, he's different. Now, he's the same, these two are the same. When you have x equals 10 to the y, that means y is the log base 10 of x. And what the hell does that mean? Well, if you read right above it, I'll tell you what it means. It means y is the exponent. I mean, that's the answer to a logarithm. Here's what it is. The answer to a logarithm is the exponent that you put on the base 10 that you put on the base, which in this example is 10, in order to get x. In order to get x. That's a long sentence, but that's what a logarithm is. What the hell is this logarithm? It's the exponent you put on 10 in order to get x. That's what it is. If I look right above it, I see that. The logarithm is the y. What's the y? The y is the exponent you put on 10 in order to get x. You know, over here in this chart, when I plugged in a 2 for the exponent, I got 100 for the answer y. But in this chart, if they're inverses, these things are all reversed. Here, let's make a chart for this dude. Watch this. And I can sit there and just reverse them, but let's try to understand it. Watch this. If I plug in 100 for x, if I plug in 100 for x, then you're staring at this, log base 10 of 100, and you're trying to tell me the answer. And what's the answer? The answer is the exponent that you put on 10 in order to get 100. There's a rhythm to that. Oh, and it's called a logarithm, and it has a rhythm to it. Maybe you didn't feel that rhythm as good as I do. I feel that rhythm. It's the exponent you put on 10 in order to get 100. I mean, I feel it. Do you feel it? Not yet? I got to keep dancing for you a little bit. It's the exponent you put on 10 in order to get 100. What is it? 2. Thank you. See, now you can do logarithms. If you say this sentence to yourself, that's what the hell, I mean, logarithms aren't strange anymore. So when you plug in 100, you get a 2. Now hang on, back over here. This was just an exponential function. This was an exponential function. What were we doing here? We were plugging in exponents and finding answers. I plugged in a 2 and got 100. Well, what am I doing over here? I'm sort of plugging in the answer 100, and I'm looking for the exponent. It's the opposite. It's the inverse. If you plug in 1,000, you're looking for the exponent that you put on 10 in order to get 1,000. What exponent do you put on 10 in order to get 1,000? 3. If you plug in a 10, you're looking for the exponent that you put on 10 in order to get 10. What exponent do you put on 10 in order to get 10?
1.
A 1. See, so when I talk to you, you understand it. If you talk to yourself like this, you understand it. It's the exponent. That's what, when you leave here, what the hell is a logarithm? It's an exponent. If I plugged in a 1, I would get a 0. If I plugged in a 1/10, I'd get a -1. Watch this. I want to plot these points. This is this function. This is this function. He is the inverse of this function, and I want you to see what happens. One of the points is 1, 0. Another point is 1/10, -1. Watch this. When x is 1/10, y is -1. When x is 10, y is 1. Watch this. When x is 10, way out here at 10, y is a 1. Instead of a horizontal asymptote, this logarithm graph has a vertical asymptote. And this graph approaches this vertical asymptote, it hits these things, and it starts cruising off this way. When x is 10, it was a 1. Watch this. What happens when x is way out here at 100? When x is 100, what is it? 2. This is a pitiful function. You know how the exponential function is steep and kicks ass? Excuse my language. Right? The exponential function is so steep it kicks butt. Well, this logarithm function is his inverse, and he's so pitiful. He's like the slowest rising function there is. Watch this. When x is 1,000, what's y? 3. Are you with me? It's rising, but it's rising very pitifully. Here he is. He's the least steep function there is. He's a logarithm. You know, there's been a lot of earthquakes in the news. And the Richter scale is a logarithmic scale. You know, when you have an earthquake that's 6.2, that's the exponent of how strong that damn earthquake was. When another earthquake is 7.2, that's the exponent. And it's a base 10 logarithmic scale. So this is 10 times stronger. Does that make any sense to you? Yes. It's 10 times stronger because it's the exponent. Maybe I shouldn't use those numbers, but like if one earthquake was a 2, that's the exponent you put on 10. When the other earthquake was a 3, that's the exponent you put on 10. When you put this exponent on 10, you get 100. When you put this exponent on 10, you get 1,000. Right. So when it's 1 unit stronger earthquake, it's really 10 times as strong. Hey, so guess what? Look at the blue picture. Look at the black picture. The black picture is this exponential growth function we studied hard last week. The new blue picture is a logarithm function. It's this guy. It's log base 10 of x. And he's the inverse of him. And maybe that triggers some memories from last week. They are mirror images of each other. And this is the mirror. Remember that? They're mirror images of each other. And this is the mirror because they're inverses of each other. So I think I just explained to you what a logarithm is. I think I just explained to you what a logarithm graph kind of looks like. It's the inverse of that graph. But to tell you the truth, I'm not going to make you graph a bunch of logarithm graphs. I'm not. Listen, I like to graph this. I don't know if you, from last week, you probably remember I graphed a bunch of these damn things. Exponential growth, exponential decay. I love graphing these exponential functions. You have to graph these exponential functions. I want you to understand logarithms, but I'm not going to make you graph the heck out of them. You hear me? I graphed this one for you. I wanted you to see the inverse idea. But I'm not focused on these logarithm graphs. I showed you one here. Okay? But I am trying to make you understand what a logarithm is. Here, try this. Log base 2 of 8. I want the answer. And you have to talk to yourself. You have to say, the answer is the exponent that you put on the base. What's the base? 2. 2's the base. The little subscript is the base. This was base 10. This time 2 is the base. The little subscript's the base. Anyway, I'm looking for the exponent you put on 2 in order to get 8. Some people just know it. You could play with a calculator, but it's not that hard. The exponent would be 3. Why? Because 2 to the 3rd equals 8. The answer to a logarithm is an exponent. Watch this one. Log base 5 of 25. This time it's log base 5. I'm looking for the exponent that you put on 5 in order to get 25. See, when I say the sentence, you get the answer. But if I shut up, you got to say the sentence to yourself. I'm looking for the exponent you put on 5. What's the answer? 2. 2's the exponent. Some students will say 5. They'll say, oh, the answer is 5 because you got to multiply by 5. But I'm not asking you what to multiply by. I'm asking you what exponent do you put on the 5 in order to get 25. And the exponent is 2. So I'd like you to understand some basic logarithms like this that you can just do in your head. But you got to kind of understand them. When they get kind of weird numbers, of course, what we do is we pick up a calculator and we do logarithms on a calculator. And then you don't understand them. You're just punching a button. So I'd like you to know both. I'd like you to understand them a little bit and know how to punch a button. We need to know both. There is no... So on your calculator, and I used to say this, and now times have changed, and so I might be a little bit in error here, but I'm going to say this. On your calculator, there's really usually only 2 log buttons. And so you usually don't have a log base 2 button, and you can't do this on your calculator. Although nowadays, you might be able to type in the damn base. But let's forget that a second. I'm saying you don't have a log base 5 button, and you probably can't do this on your calculator. But what you do have on your calculator is 2 very famous logs. And they are log base 10. Log base 10 of x. He's so famous, he's used it a lot in chemistry and science and earthquakes, and he's used it a lot. And since he's used a lot, sometimes we call him the common logarithm. Common logarithm. I've heard that phrase. Don't worry, I don't think that'll come up again. But anyway, he's famous. He's log base 10. And then sometimes we write log without the base. So if you see an log without the base, you can assume it's base 10. Thank you. That's also a little new to me. When I was studying this stuff in kindergarten, I'm kidding. But when I was studying, I was kidding. When I studied it, it seemed like we always wrote the base. I don't think we had this rule that says, oh, you don't have to write the base. Anyway, we would always write the base to indicate what base it is. But apparently, they got sick of writing log base 10. If it's log base 10, we can just write log. And then here's the other famous one. Log base e. And I kind of told you about this last week, and nobody ever writes log base e. Instead, this is known as the natural logarithm. And we write the ln of x. The ln sort of standing for logarithm au naturel, maybe. But natural logarithm. So those are on your calculator. You should have a button for that. You should have a button for that. And I just wonder if you can do this for me then. The log base 10 of 8, 5, 4, 7, 2, 6. And this is not one I would ask you to do in your head. This is one you would definitely just pick up a calculator and tell me the answer. When we do this, we tend to round to 3 decimals. We kind of like to do 3 decimals on these guys. So can you find your LOG button on your calculator, and can you type in 854,726 and tell me the answer?
5.93.
5.93. Let's go one more decimal. 2. If you round it to 2. 2. You guys okay? You found your button? Okay, listen, so part of this test, man, is knowing your calculator and using your buttons. I mean, so do that before Tuesday. Listen, I can't help you right on during test. You can't say, help me learn how to use my calculator. I can't help you during a test, but a couple weeks before the test, I can help you use your calculator, show you how to use it, find your button for you, help me use it. Well, now you kind of know what a logarithm is. Let me say something else. I could have kind of done this one in my head. Well, not exactly, but I want to show you something. Watch. You know, what are we looking for here? What's the answer? I mean, don't tell me the answer, but the answer is the exponent. We put on 10 in order to get that huge number. And see, so watch this. So I'm playing around. I'm going to play around. What if you think it's a 2? You guys think the exponent's 2? What if you put a 2 on it? What do you get? No, I guess that ain't it. What about a 3? You guys think it might be a 3? Nah, I guess that ain't it. You think it could be a 4? No, that would be 10,000. That's not quite it. Do you think it could be a 5? Well, that would be 100,000. That's not quite it. Do you think it might be a 6? Well, a 6 would be 1,000,000. So, what am I trying to get? I'm trying to get somewhere between 100,000 and 1,000,000. I'm trying to get, and it's closer to 1,000,000. I'm trying to get 854,726. So, how did my exponent, what did the answer come out to be? Something between 5 and 6. And pretty darn close to 6. You understand this? This is a nice little explanation. I mean, this 5.9 is not all that mysterious. It's the exponent you put on 10 in order to get 854,000. You with me? You can try it, by the way. You try 10 raised to the 5.932. Do you get that number? Do you get that number? Right, you don't get it exactly. He said pretty close. You won't get it exactly, and why not? Why? Can you explain to me why it didn't come out perfect? Because this was rounded to begin with. Thank you. So this was rounded, and we put it on there. We don't quite get back to the original because this was rounded, right? Cool. Logarithms are the inverse of these exponential functions. That wasn't bad, you guys. I just explained to you what logarithms are. I hope that was kind of quick. I hope you understand it. Let's keep talking. If I go to 5.4, there's these special properties of logarithms. This is, these are kind of funny, and I tend to de-emphasize these a little bit. You might see them on my practice. You might see them on next week's test. You might see them on my practice. I don't even think they show up. Anyway, watch. There's three, they're funny properties. They're interesting as hell, really. If you have the log of an A times a B. Now, by the way, which log did I just write? I wrote a log. I say the word log, but which one is it? It's the natural log. The truth is, these properties work for any log. So I could have wrote log, or I could have wrote log base 2, or I could have wrote log base x. I mean, these properties work for any log. I prefer ln because it's a little shorter bit of writing. Just one letter shorter. But here's the property. If you have the log of two things that are multiplied, you can turn it into the log of A plus the log of B. It's kind of strange, man. The log of a product can get turned into the sum of two logs. Here's another property. the log of division can get turned into the log of A minus the log of B. Now see, y'all figured that out, didn't you? It's kind of logical, I guess. These are funny properties of logarithms. I want to say that nothing else in mathematics acts like this, but does something, can you think of something that sort of acts like this? What takes multiplication and turns it into addition? What takes division and turns it into subtraction?
Exponential function.
Well, your laws of exponents. When you have, but the rule is when you're multiplying like bases, what do? Add the exponents. So there is something in math that does kind of act like this. When you have, when you're dividing like bases, what do you do with the exponents? Subtract. And if you recall, what did I say these logarithms are at their core? What is a logarithm? An exponent. So these properties of logarithms resemble properties of exponents, and logarithms are exponents. This is a lot of heavy stuff I'm laying on you, but you got time to digest it. Heavy. It's like a heavy pound cake. Hey, there's one more cool property. This is my most useful one. I'm putting a little asterisk on this. It says this. When you have a log of something that has an exponent on it, you're allowed to take that exponent, p, I call it power, like a power, p. I'm allowed to take it and multiply it down front. So it's p times the ln of a. When you have an exponent on what's in your logarithm, you're allowed to pull it down front and multiply it. Special properties of logarithms. That sort of resembles this. When you have an x squared raised to a cube, when you have an exponent raised to an exponent, do you know what you do when you have exponents raised to exponents? That's when you multiply the exponents, which is kind of like this guy coming down and multiplying this thing. Right, you get x to the sixth. You know, here's some other little properties, but these are these three kind of important properties. You know, the other thing I'm doing, you guys, we're at the end of this class. We're studying exponential functions and logarithm functions. Anyway, in your next class, if you go on and take more algebra, pre-calculus, they study this stuff again. And you might hit a little tougher problems. They might hit it a little deeper. It's a little, anyway, I'm giving you a college algebra version of this. And then there's a pre-calculus version of this. They might make you work with these properties a lot more. That's why I tend to just minimize them a little bit. They work with them a little more in the next class. So we're kind of on the edge of the next class here. But you know, so these logarithms are inverses of exponential. They cancel each other out. I taught you that last week, actually. Like if you have the ln of e to the anything, the ln and the e cancel each other out, and you get x. I sort of taught you that last week. I was trying to solve for x, and I had to kill the e, and this is what I did. But it works when the bases match up. See, what is the base on this ln? What's the base on ln? We don't write the base on the ln, but what is the subscript right there? It's e. So when the base is e, and then it hits this e, that's when they cancel each other out. So what about this? What about the log base 10 of 10 to the 7th? I mean, that looks like a complicated thing, but you should understand that the log base 10 is the inverse of the exponential function base 10. And so the log base 10 kills the exponential function base 10. It's like they cancel each other out. They undo each other. What's the answer? 7. I don't know if you call these properties, you might call these properties. It's just that it's the concept that they're inverses of each other and they cancel each other out. I mean, the analogy is, if someone says you got an x squared and you square root it, it cancels each other out and you get x. All right, I might need this property 3. I might need to elaborate on this. There's another thing here. Let me say another thing here. I'm not a big fan of this, but I think it shows up in 5.4. It's called the change of base formula. So this is one more formula. You might need it on your homework. I don't think you need this on my test, but watch this. You can take any logarithm of any base. So I'm making a logarithm base b of x, and I can change it to any base I want. And so what base do you want to change it to? Again, you're very new at this, I realize that, so you can't answer all my questions. But there's 2 super famous logs that are on your calculator that we all love to use. There's log base 10 and log base e. So if you have like a log base 17, you might say, screw this, I'm going to change the base to one of my famous. These are on my calculator. These are easy to find. They have a button. So I might want to change this to log base 10 or log base e, either one. And so I'm changing it to log base 10. So here I go. The formula is I'm changing it to log base 10. I'll put a little 10 there. And I do the log base 10 of the x over the log base 10 of the b. That's the change of base formula. But I didn't have to change it to log base 10, so I'm going to do something else here. I could change it. I'm going to put a little or here. I could change it to the natural log. The natural log of the b, the natural log of the x over the natural log of the b. It should be the same thing. Let's just try one. So if I ask you to do log base 4 of 37, the truth is, if you're good at your calculator and you're investigating your calculator, you might find a way to just type that damn dude in. But I'm suggesting that you don't have a button for log base 4. You can't do this. And so I'm suggesting maybe we should change the base. So you could do log of the 37, that'll be some decimal, divided by log of the 4. That'll be some decimal. And when you divide those decimals, you'll get an answer. Can somebody help me do that? Can you?
1.789.
That's your final answer? Or that's your numerator?
That's what I got.
I mean, you did both these steps. You did this, and you divided by this. And your final answer is?
2.605.
So be careful. Let's see. So parentheses sort of help when you divide. And the truth is, it doesn't matter if you use your log button. Your log button is base 10, or you could use your ln button. They should be the same, although that numerator is different than that numerator, and this denominator is different than this denominator. But when you divide these answers, it should be the same thing. And I'm saying, you're saying 2.605. Thank you. By the way, I can sort of check it. See, I know these numbers seem very mysterious, but one more time. The answer to this is the exponent you put on 4 in order to get 37. Listen, if it's 4 squared, what is that? 16. If it's 4 cubed, what is that? 4 times 4 times 4. 64. Anyway, I'm trying to get 37. So it must be, the exponent must be between 2 and 3. And it was, according to you guys. All right. Hey, we're doing great, you guys. We're doing great. Let's do this. I'm heading into 5-5 now. And the truth is, we already did a little 5-5 last week without you even knowing it. Listen, I want to solve exponential equations. So here we go. If I have this exponential equation, watch this. Here, I won't make it too hard. E to the negative 3x plus 5 equals 28. I want to solve for x. That's what happens up in 5-5. And to tell you the truth, I actually taught you this last week. I want to solve for x. And before you even knew about logarithms, I taught you how to use logarithms to help you do this. This ain't that bad. This is so. I know I'm moving fast today, but this stuff ain't that bad sometimes. Look, to solve for x, I think I would try to. I think I'd subtract 5. Do you agree?
Yes.
Okay, thank you. So now I have this e to the negative 3x equals 23. So now you have to undo the e. The way you would undo an e or kill the e or cancel out the e would be using a logarithm. And by the way, which logarithm? The natural logarithm, because it's base e. Good job, right? So now what do? You take the natural logarithm of both sides. So you take the natural log of this, and you take the natural log of this. Now, I warned you last week, some students look at that and say, oh, you multiplied by the ln. No. That ain't really, multiplying ain't what I'm doing. I'm taking the natural log of this quantity. Multiplying is not really what I'm doing. But on this side, what's the point? The point is the natural log kills the e because they're inverses of each other, and you're left with negative 3x. On this side, I would just wait, but it's just a decimal on your calculator, but I wouldn't decimalize it yet. I just wait a few seconds. I'm trying to solve for x. One more move. One more move is find x. Divide by negative 3. See, when you killed the e, this thing that was up in the air fell down to this line. It's now on this line. You know what you could think? Well, you could think you just did property 3. You could think that you just brought this down front. That's one way to think of it. It's better to think of it as canceling, maybe. Whatever. If you brought it down front, then you'd still have the ln of e, but the ln of e cancels out, you get a 1. So you still get this. I don't know. Now I'm making you think too many different ways, maybe. I like to think that the ln cancels the e and you just get this. And then you divide by negative 3, so x is this answer. And you know me, sometimes I like my exact answers. And guess what? That would be my exact answer.
So you don't put a decimal?
Well, hold on. I want both. But I'm trying to, the semester's almost over. I still want you to know the difference between exact, which is mathematically symbols that are exact, and approximate, which means you picked up your calculator and you decimalized it. That's approximating it because you're going to round it off. But I do want that. Because I want to see if you can use your calculator. So I do want both. So there's my exact answer, and what's it approximately equal to?
Negative
1.045.
Negative 1.045. If you go to 3 decimals. Thank you very much. You did that natural log of that number. After you got that, you divided by negative 3. So cool. Hey, you can solve exponential equations. What about this one? Can you solve that one for x? I want to solve for x. See, it's called an exponential equation if it's got the variable up in the exponent, which is what this chapter is kind of all about. So we got an exponential equation. Can you solve for x? I think you want to use logarithms. Which logarithm would you use this time? Because it's a base 10, I think you should use log base 10. And this one's real easy. There's no extra steps. On this one, I think I got one move to do. Take the log base 10 of both sides. Take the log base 10 of both sides. The log base 10 of this 10 cancels out and you get x. And the answer is right there. The log base 10 of 528. Remember, if I don't write the little 10, you know it's log base 10. But anyway, there's the answer. But can you use your calculator to help decimalize that, please?
2.722.
2.723. This time I'm using the LOG button, the log button. All right, listen, here's one more. So when it's base E, we love to use, we use a logarithm, but we use the natural log to kill the base E. It's very logical. When it's base 10, we use the LOG base 10 because that kills the base 10, right? Very logical. If it's some other weird base, watch this, watch this, watch this. If it's a 7 raised to the negative 2x equals 143, see, now I got to kill the base 7. So maybe your logic is, if you want to kill the base 7, you should use a log. Which log should you use? Log base 7? I mean, maybe you should use log base 7 to kill the 7. That's the logic, you guys. To kill the E, we needed log base E, which is called the natural log. To kill the 10, we needed log base 10, which is just log. So to kill the 7, maybe we need log base 7.
So whatever the base number is, what the log number?
That's the log that will kill it. Are you guys okay? All right, now hold on. I got an issue with damn log base 7. The way I was raised, you don't have a damn log base 7 button. So now, I don't like log base 7 because I ain't got a log base 7 button on my calculator. Well, if I made it a log base 7 problem, I do have, she keeps pointing to this, I got a change of base formula. So if I do have a log base 7 problem, I shouldn't freak out. I could use my change of base formula. Except when I was a kid, I didn't have this. I don't know why. I didn't know about it. All right, listen, I'm sort of talking out both sides of my mouth here, but listen to me. Here's what I want to say. Here's what I want to say. I want to say you can use any damn logarithm, but it's a little different strategy. So here's what I'm going to do. I'm going to use the ln. Now watch. So I'm going to take the ln of both sides. Here I am with this problem. I'm going to take the ln of both sides. So when I take the ln of this, now guess what though? It ain't going to kill it. It is not going to kill it. Because an ln is base E and it won't kill the 7. So I'm not canceling this. I'm not going to cancel it. It's not working for me. But you know what will work for me? This property 3. So I just took the ln of both sides. The ln won't kill the 7, but I can do this. I can take this exponent and bring it down front. That's what property 3 says. So watch this. I can take this negative 2x and bring it down front. That'll let me solve for x. Watch. I'll have negative 2x in front of this ln 7, and it equals this ln of 143. That's using that property 3. I didn't practice these properties too much with you, and you haven't practiced them much, but it's valuable. This property 3 is kind of valuable because it brings that exponent down front. Now listen, can you solve for x now? Can you solve for x now?
Yeah.
See, it looks confusing, I know, but you got to keep in mind that ln 7 is just a number, and so I would divide by it. And that negative 2 is a number. I would divide by it. So if I divide by both of those, my x is, what's on the other side? The natural log of 143, and I want to divide by the negative 2 and the ln 7. I just divided by both of these guys to get x by itself. Be careful, if you want to type this in your calculator, you might need parentheses here. I think that might be important. Those parentheses up top are a little redundant there, but be careful and maybe you can tell me this answer. hard for me to, I can't even, I don't know.
Is it negative 1.275?
9.668.
Okay, I got negative 1.275. I think I'm right. So what do you got to do? Like I said, when you divide by 2 multiplied things, parentheses help. Otherwise, your calculator might think you're just dividing by him and multiplying by him. So parentheses help tell your calculator you're dividing by all that crap. I think this is the answer. So what did I do? Instead of killing the base 7, I just did any logarithm I wanted. My favorite logarithm is ln, because it's easy. So it's on my calculator, it's easy. So I did the ln on both sides. Did the ln kill the 7? No, it did not. But it did allow that exponent to come down front, thanks to good old property 3 of logarithms. I get that exponent down front, and now I can solve for x. Now I can solve for x by dividing by those other numbers. That's the strategy. That's that strategy. It's a little different than those other strategies. Well, the strategy for this was use the base 10 to kill the base 10. But on this one, I didn't want to use a log base 7. Because I don't like log base 7. I don't know what the hell it is. You follow my strategy? You with me? You could have used log base 7. Watch this. Same problem. Watch this. All right, you want me to use log base 7? Okay, I'm going to do log base 7 of 7 to the negative 2x. I'm going to do log base 7 of 143. Okay, this time I'm not thinking about property 3. Now I'm thinking that log base 7 kills the base 7. So it just kills it. And I'm left with negative 2x. But on the other side, I have this log base 7 of 143. Which, again, I search on my calculator and I don't have a log base 7 button, so I'm not real happy. But you know what? I do have a change of base formula. The change of base formula says I can change it. Let's not do this one. I could do that one, but I could do this one. I can change it to the ln of the x over the ln of the b. What would that be? That would be the ln of the 143 over the ln of the 7. You guys okay? One more move to get x. Divide by negative 2. So x is that ln of 143 divided by negative 2 ln 7. Guess what? That's the same answer I had a few minutes ago. Same answer I had by my other method. This is a lot of stuff, real quick. You have to go digest it a little bit. I think this is easy. When it's base E, I think you know what to do. When it's base 10, I think you know what to do. I think you got a little mad at me when I went to base 7. But I've tried to explain it. It's a little different. With base 7, I got a couple different strategies I can use. Back to these properties. So I took a leap up into 5.5 for a second and tried to solve some exponential equations, because that's what 5.5 is. I'm going to go back to 5.4 a second. Again, watch this. This is a typical problem that makes you work with these logarithms. Watch this. If I give you the logarithm of x squared y cubed z to the fifth over z to the fifth. See that, how I wrote that? The natural log of x squared times y cubed all over z to the fifth. Then what they want me to do, they have these exercises that say, bust this up. And that's not exactly the words they use. I would say, bust this up. But they say, use these properties to bust it up. Or, what do they say? Rewrite this using the properties. Rewrite it as a sum or difference or multiplication of logarithms. So they want you to use these properties. So, do you see some multiplication in here?
Yes.
Well, then you can take that multiplication and rewrite it as the sum of two logs. So I'm going to write the ln of x squared plus the ln of y cubed. Do you see division in this problem? Do you see it divided by z to the fifth? Well, that would be, I can subtract that denominator. I can subtract what's in the denominator. So I sort of just use property 1 and 2 all together here. Can you handle that? I just used property 1 where I had the multiplication, and then where I had the division, I subtracted that guy in the denominator. I used both those properties real quickly there. That wasn't too hard. I got one. I could use property 3 now. What property 3 says, if you got any damn exponents, you can multiply them out front. So I can bring this 2 and write it like this. I can bring this 3 and write it like this. I can bring this 5 down and write it like this. And I'm done with this problem. And it was just an exercise in using properties. It was just it's like, go home and do some push-ups.
You can't finish it then?
Well, there's nothing to finish, right? There's no solving. This ain't solving. It's just kind of rewriting, just sort of push-ups that make you practice using these properties.
Do you have that on your desk?
I think it shows up in the homework. It shows up on my practice.
How about the quiz?
I don't know about my quiz. And I don't think it's on my test. It's just, yeah, it's not that important. But it is exercises to help you learn these properties. And it's more important in the next class. They'll make you do more of this. But it wasn't hard, was it? Just using these properties. Take this and bust it up. By the way, you can use these properties backwards. So you might have some questions that say, take this and put it back together. See, you can use these properties backwards. So guess what? You could take this 2 and say, oh, I'll put the 2 back up here. And I'll put the 3 back up here. And then, oh, if I have addition, I can take the addition and put it together as one logarithm. If I have subtraction, I can put it together as one logarithm. So you can use these properties to bust this up, or use these properties to put it back together. And they got exercises that make you do both, probably. But I don't want to, I'm de-emphasizing it a little bit because I'm not going to practice 12 of those. Now, what did I practice 3 or 4 of? Solving exponential equations 10 minutes ago, right? I solved several of them. I was a little more enthusiastic about that. I should have like an enthusiastic meter so you can tell what's more important and what's not more important. But you should tell. You should be able to tell. I communicate that fairly clearly, I think. You know, let's do this. Okay, yeah, I forgot this. In 5.5, one more little thing here. Actually a couple more things. But in 5.5, one little thing. They said, let's solve exponential equations. So I did 3 of those a few minutes ago. That was before this. I did 3 exponential equations. We solved it. Base E, base 10, base 7. We tried all 3 of those. Now, you also, in 5.5, get to solve a logarithmic equation. And I don't make these too difficult. I want to show you what it is, though. If I want to solve a logarithmic equation, it might look like this. Log base 6 of 4x minus 7 equals 2. And that looks scary. It looks weird. It looks strange. And you're supposed to solve for x. It's an equation. You can tell it's an equation. And you're supposed to solve for x.
And you do the third property before
Not really. There's no power up here to bring down, but here's what I'd like to do. I want to do this thing where I rewrite this. I rewrite it as an exponential function. If you remember when I started this logarithm discussion, there's a base raised to an exponent equals, look. You know what you need this in your, you need this in your back pocket. You need this idea. Either this idea or pick your own. What's the answer to this? Log base 2 of 8? The answer is 3. Because it's the exponent you put on 2 in order to get 8. 3 is the exponent you put on 2 in order to get 8. Or you could say because 2 to the third equals 8. Now look what I did. I just rewrote that. Look, the base is 2. We all know the base is 2. And we should know that the answer is the exponent that you put on 2. And then it equals the 8. So if I rewrite this, what's the base? 6. The base is 6. The exponent that you put on that base is the 2. And it should equal the 4x minus 7. So as soon as you rewrite that, which is a kind of an important part of understanding logarithms, is to understand how to rewrite them. But as soon as you rewrite it, dude, you got the easiest problem in the world, don't you? I mean, if you're trying to solve for x, it looked scary a few minutes ago. As soon as you rewrote it, this is nothing to this, because 6 squared is what? What's 6 squared? 36. Like I said, this is the easiest problem in the world. You add 7, divide by 4. You know what I mean?
Isn't that 29? You minus 7? Oh, you add 7.
I added 7.
Never mind.
Yep. All right. That's a cool little problem. Anyway, here, let's do something else. Before last week we were working on these interest problems. These interest problems are good stuff. I gave you these 2 formulas. One of them is this. This is about money in the bank earning interest. This is when it's compounded n times per year. And you should understand how to use this formula. I told you I'd give it to you, though. You don't have to memorize it. And then there's this other formula we learned also about money. It was P e to the RT. This is when you're compounding the money, you're compounding the interest continuously. When you compound a certain number of times per year, that's n, and you use that formula. But when you compound continuously, you just use this formula. The word continuous is kind of an important word. But then, I mean, here's a classic. We worked at this. This is in 5.2, but it's going to connect to something here in 5.6, so bear with me here. So if I said I have $15,000 and I invest it, and it's going to earn 7.8% interest, compounded continuously. If I tell you that, then I've given you some information, and now I have 2 questions. Part A is, how much money will I have, or will this be? What will this is going to grow. This money's going to grow. How much money will I have in 20 years? So that's a good question, and that's not too difficult. A calculator is helpful. We do use a calculator. But here's part B, and I said this last week. When will I have $1 million? So we did this last week. Let's do it again. This is big. This is big. This is all over my test. This crap. I mean, this is all over, everywhere. All right, so it's pretty easy. By the way, which formula should I use, you guys? Which formula should I use? The second one. How come? Because it's compounded continuously. The word continuous. Yep. Okay. So then I use that formula. So, and do I know what? I'm looking for how much money. That's the A. The P is the original amount of money. What's that? $15,000. E raised to the R. The R is the interest rate. What is this? There it is. But you write it as a decimal. So you move the percentage. It's a percent, and you write it as a decimal. So it's 0.078. Right? If you need an example in your brain, like 12%. What do you do with 12%? You call it a 0.12. You move the decimal over. So what do you do with a 7.8%? 0.078, I think. You move the decimal over. Times T. What's T? The 20 years. Yep, the 20 years. Bing, bang, boom, boom, bang, bing. You put, this is a calculator problem now. Be careful though, get organized. You need your E button. You need to raise it to this power. Maybe you need parentheses on all that, you guys, because that's all in the E. Then you multiply by 15,000. Some of you type it all in just like this. Some of you do little baby steps. You multiply that, then you E it, then you multiply by the 15,000. I mean, I want you to, it's a shame to screw up this test because you can't use your calculator, so you gotta practice that. What's the answer? Anybody? What? 71? Might be good.
71.
I did leave it. That's pretty good. 71,000. Go ahead. 382 point. And now I want 2 pennies. I mean, I want 2 decimals for the 32. Cool. 71,000. That's pretty good. I had my $15,000. I left it in there for 20 years and it grew. Thanks to that 7.8% interest, compounded continuously, my money grew pretty good in 20 years. You guys with me? Okay, and then the next question is awesome. See, the next question makes you solve an exponential equation, which we were working on 10 minutes ago, 15 minutes ago. When will I have $1 million means you plug in 1 million for this. This is still the 15,000. This is E. The interest rate is still the 0.78, but what's the unknown? Thank you, the when, the T, the time. How long will it take? Well, it's going to take 20 years, 30 years, 80 years. Right, we're looking for T, right. So now we're solving for T. And we practiced it a little last week. We could practice it again today a little bit. How do I solve for T? You got to expose the E, so you got to get rid of that. You got to,
Natural.
well, you do need a natural log, but not yet. You got to get the E exposed. So divide by the 15,000. It is a multiplied 15,000, so please divide by it. If you divide by 15,000, it's gone. It cancels. You're left with E to the 0.078 T. We're trying to get T. Over here I got, I can cancel 3 zeros. You guys, that's 100 over 15, isn't it? Wait, whoa. I didn't have enough zeros. Hang on. Yeah, when you write 1 million, make sure you write 1 million. Damn it. You guys with me? I screwed up on my million there. So what do I got? 1,000 over 15. 1,000 over 15, you can divide that. What is 1,000 over 15? What is it? 6.6666? Or 66?
Oh, 66.
66.666666666. All right. Well, that's cool. I guess we got to round it somewhere. All right, so this is rounded, which kind of bothers me, but that's okay. If I take, now what? I'm trying to get that T. What do? I got to kill the E. Logarithm. Which logarithm?
Natural.
Thank you. ln. I need to ln both sides. natural log, ln, 66.67, and I got to ln this e thing over here. Lnning the e cancels the e and leaves me with the 0.078t. I'm close. I'm so close to being done. What do I got to do? One more thing. Divide by the 0.078. Right, you guys? So the answer is this natural log of 66.666666, or however you want to write it, over a 0.078. Now, depending on how many damn sixes you type, you might get a little different answer than somebody else, but it might not be much different. So if you went with what I wrote, can you type that in and give me an answer? I'm thinking it's 60, 70, 80 years. I mean, 20 years, I don't know. What is it? Maybe 100 years. I don't know. What is it? Have we got an answer? 50? 53.8 years. When it comes to this, I kind of like, when it comes to these years, I like tenths of a year. I don't need, that's good enough. 53.8 years. Good job. All right, listen, I got 7 minutes. I got one more important thing to teach you. It's totally related to this. You ready? But here's what happens. The reason I wanted to do this was really back in 5.2, and it was about money. I want to tell you what happens in 5.6. And this is the last section of the book, you guys. We're done. The semester's over. In 7 minutes, the semester's over. Well, except for a bunch of testing and finals and all that. In 5.6, here's what they do. They do some more word problems. Okay, listen, money's not the only thing that grows exponentially or decays exponentially. So things in the world, populations grow and decay, and so we can have other word problems. But if we use the word continuous, then the formula looks like this. They use, what do? They do y equals y with a subscript 0 e to the kt. Now what does that look a hell of a lot like? Doesn't it look like that? I mean, A is the final amount of money, P is the original amount of money. When somebody uses a subscript 0, that means the original amount. I mean, this is the same problem. Instead of an interest rate R, I got some kind of a growth rate K. Are you following me? This is the same formula. But we apply it to other things besides money. So like this, like this. There were, watch this, there were 1,000 roaches in my kitchen. Did I already do some kind of gross problem like this? The first day I did. Anyway, more gross stuff. Anyway, there were 1,000 roaches in my kitchen. I sprayed them. I sprayed with a deadly organic chemical. Deadly organic something. I sprayed. They began to die. They began to die. Watch this. To die at a continuous rate. Continuous. I'm using the word continuous. That kind of clues you in on the formula. They died at a continuous rate of 36% every hour. This is awesome, you guys. By the way, this happened. This happened at 6 a.m. this morning. 6 a.m. this morning. That's when this problem started. So at 6 a.m. this morning, what do you want to call your time? 0. I think you want to call that time equals 0 at 6 a.m. So 7 a.m. would be 1. 8 a.m. would be 2. So I might have some good questions here for you, but the first question is, can you write an equation for these roaches? So part A is just write an equation. That's all. And then part B might be, how many roaches at 8 a.m.? That's a good question. And then part C might be, watch this, when is there one dadgum roach? These are good questions. 3 cool, good questions finally before the semester ends. I got some of these on your practice piece of paper too, by the way. We got a few minutes. Relax. Let's finish this. This is pretty darn easy. It's this equation, you guys. What goes right here? What's this y naught? The starting amount. Thank you. The starting amount. That always goes right there. So I'm going to write an equation. Y equals 1,000 roaches. E. So what about the K? The K is the little growth rate or decay rate. Decay, it's a decreasing. Or, well, by the way, what's happening to these roaches? Is their population growing? Oh, they're dying. Thank you. I sprayed them and they're dying. So this is exponential decay. And anyway, the rate would be 0.36, but because they're dying, I'm going to put a negative. Negative 0.36. So it's real subtle. If this was a growing population of roaches, it would be a positive 0.36. But this is a dying population of roaches. We'll put a negative 0.36 t. We don't know t. See, that's when I say write an equation, you have a y and a t and a couple things filled in, and now you're ready to use this equation for the other 2 questions. You with me? And by the way, when t is 0, plug in a 0. When t is 0, what do you get? E to the 0, which is 1 times 1,000. You get 1,000 roaches. That's when t is 0, when this problem started, you get 1,000 roaches. And by the way, 6 a.m., t is 0. All right, so what do you want to do with this question? How many roaches at 8 a.m.? What do y'all want to do?
So do you plug in E for T?
Plug in a 2. I mean, thank you. Right, you guys are smart. You can do good on this test. You can do this stuff, but you better practice it. That's awesome. You plug in a damn 2. Thank you. By the way, be careful with your order of operations. You know, you got to multiply by 2. You got to E it. You got to multiply by 1,000. Maybe an extra set of parentheses here kind of helps you. I don't want to confuse you, but I'd like to know what the answer is. Hopefully it's less than 1,000. See, here's how I'm going to do it. Negative 0.36 times 2. That's a negative 0.72. I'm going to E that. I'm going to E that answer. And then I have to multiply that by the 1,000. So then I get, oops. What'd you guys get? 486.75 roaches. Okay. I'm glad I left the house. How long will it take for there to be one goddamn roach? That's a tough sucker too, boy. He won't die. He won't die, that damn son. What should I do?
Put the 1 in for Y.
Thank you. You put the 1 in for Y. Yes, ma'am. It's like when I asked you how much, when will it be $1 million? You put the $1 million in for Y. This time, when will it be 1 roach? You put 1 roach in for Y. This is 1,000. This is E to the negative 0.36 t. And now we got to solve for t. And we've been practicing this. It ain't too bad. What should I do? Talk to me. Divide by 1,000. If you divide by 1,000, you get a little 0.001 if you want to talk like that. When you divide by 1,000. 1 divided by 1,000. Equals E to the negative 0.36 t. What do y'all want to do now? Natural log both sides. I love it. I love it. I love it. Natural log both sides. The natural log over here is going to kill the E. It's going to leave me this. You guys understand? I did a natural log of both sides. On that side it killed the E, on this side it's sitting there. One more move to get T. Divide by that negative 0.36. When you do the natural log of 0.001, I think it's a negative number. And then when you divide by the negative 0.36, I think you'll get a positive answer.
19.
And it may be several hours.
19.
19.2? I don't know, what is it?
188.
Oh, 19.2 hours. That ain't bad, dude. So I'm safe to go back to my house at, what the hell is that? About 2 or 3 in the morning, maybe. I'll be down to 1 roach. Hey, thanks for listening. Before you run away, I got a few things to hand you. I appreciate your attention. Uh-oh.